Oh, I'm so sorry. This portion I have missed recording. I've just started the recording and all right. So it is clear to Prasanna. What about others? Is it clear to you? Or should I repeat once? No. So basic idea about HDFS is that you take a file, split it into small pieces, and store these pieces onto data nodes, onto uh, you know each piece will go to, or each chunk will go to the one data node, and there would be a replication of the each chunk, and another chunk will go to another data node, and so on. And this information, that the which file has got which all chunks, and what all chunk is which chunk is stored on which data node, is stored in name node. So whenever you're asking for a file, you can also ask for a chunk. Say you are building a video recording system, video like YouTube. You are planning to build a system where you are running a system. Okay, so now everybody is in the line. Okay, now if you are building a system where, like YouTube, where you have to you know play a video, and then you also want to distribute the load so that one system does not get hurt in case the video becomes popular. In those circumstances, it this whole the philosophy of converting a file into chunks helps you a lot, because first chunk you will be accessing from one node, another chunk you will be accessing from the another node. All right. And this, other than that, we have got, okay, so in HDFS, other than this basic philosophy of dividing a file into chunks and storing it on the data node, the other big aspect is the failure. In case any of the data node fails, the same piece, because it is available also on another node, if the replication is more than one, then that same chunk is going to be available at two places. All right. And therefore the same chunk will be replicated if one data node, if say one node is lost. Now HDFS will notice that some of the chunks have got lesser replication than the configured one, and therefore some mishap has happened, meaning one of the node has gone down, and it will start replicating all those lost pieces from the one data node which is containing those pieces onto a newer one. And thus this rebalancing will keep on happening in case any of the data node goes down, right? So hope it is clear now to all. So Jagannath, are you able to hear now? Great. Hi Jagannath, can you hear me? It's the first day, so it might be little problematic to you guys. Prasanna, Meenal, Karthik. Jagannath, can you hear me clearly? Please introduce yourself if you can hear me clearly because you're joining just now. All right. Great, great. So Jagannath, could you just introduce yourself? Because in the first session there were so many people, so we could not. Okay. So Jagannath, feel free to introduce yourself. And so we were just discussing about HDFS architecture, and so I just did a quick recap of what is HDFS architecture. Now I'm moving on to the another one. Okay, great, great to have a great team. And Jagannath is working TCS and working on BI. Excellent. So that was pretty much about HDFS architecture. We'll go into more details later. Now, a quick recap about job tracker and task trackers. Okay, let me just do a very quick recap about job tracker and task tracker. So similar to HDFS, there is one master node like name node, and there is a slave nodes which are called data nodes. While master just keeps a record of the chunks which are being stored on data nodes. And also, whenever there is a shortage of replication factor, the data is replicated to another node. In case one node goes down, the same data which got lost is replicated to another one. So similar to that one, we have got job tracker and task tracker. So the first problem was the storage, which is solved by HDFS. Second was the computation. So for computation, we need multiple computers to do your job. Okay. So first node is your job tracker. One node is a job tracker whose only job is to take care of the task which you are assigning. All right. And get it executed via task trackers. So whatever job you are assigning to job tracker, it gets divided to task trackers, and each task tracker executes your task on a smaller set of data set and then gives back the result. In this process, in case one of the task tracker goes down, the same job is shifted to another task tracker, or same task is shifted to another task tracker, and that's it. And if that too fails and there is a time limit, then after some time it says that it could not execute the job. In case it is not, the whole process of execution of task goes beyond a certain acceptable limits. Now you have got a job tracker and you have got a task tracker. So if you assign a job to job tracker, you also specify that I am trying to process this file. Now job tracker will send your task, whatever task you has assigned to job tracker, to only those nodes which contain the data, okay, or to the nodes which are free. In case it is not able to allocate your task to a task tracker which contain the data node having the file which you are trying to process, it will not run. Okay, it will not run. So why is there is an audio problem? Okay. Okay. So I'm sorry. Now, so you say you have a big task, you have to process a particular file. So you give that task to job tracker. Job tracker assigns it to only those task trackers which are closer to the data node containing the chunks of that file. As I told you in HDFS, while describing HDFS, each file is stored on different in small chunks on different data nodes. Now, since this file is quite huge, it makes a lot of business sense to take the logic to the file. Even the small chunks, if you transfer them from data node to task trackers, it will take a lot of time. So it does that optimization so that it doesn't have to transfer that data from data node to task trackers. Okay, so the first job the job tracker does is when you assign it based on the file you are trying to process, it will ask the name node, because job tracker knows about the name node. When you're configuring any job tracker, you tell it about the name node, and once you tell that, it goes to the name node and then ask that name node, where is your file stored, on what data nodes, and then from that one it figures out which are the task tracker, which are the nodes, which are the computers running the task tracker. So task tracker is a daemon as in as a process on running on listening on a particular port, and job tracker is a daemon, data node is a daemon, and name node is a daemon. So all of these four things are running as a service on all the computers. And name node, since it has the details about where your file is located, will tell you that these are the data nodes. Now job tracker knows your topology of the network, that which nodes are far from each other, which nodes are close to each other. Okay, we will discuss the topology maybe later, but you can define the topology in the form of a big tree, and it quickly does a search in that tree, which is basically a tree symbolizing your network, and figure out that which data node is closest to the task tracker, or which task tracker is located very close to the file which is being processed, and hence the data transfer will be almost zero. And why we are talking about this data transfer? Because whenever we deal with processing huge data, we are talking about hundreds of terabytes of data or terabytes of data, and to transmit terabytes of data over the network takes maybe a day, and therefore it makes a perfect sense to do the execution near the data, take the code to the data rather than bringing the data to the code. It's like taking an X to the tree instead of bringing the tree to the X. Okay, so tree is your data and X is your code. So so that's what is being done mostly in most of the big data solutions. You do not your code is far is smaller than the data, and therefore it makes a lot of sense to transfer the code, take the code to the data instead of bringing data to the code. All right, now now there is something called Hadoop 1.0 and Hadoop 2.0. In Hadoop 1.0, there was HDFS, and on top of HDFS, there was MapReduce. Okay. Now here we only talked about job tracker and task tracker. Okay. There another aspect of MapReduce paradigm where the input is broke. You write two kinds of function, map and reduce. Okay, and using those map and reduce, you try to express your logic, and that map and reduce is being run on task tracker and job tracker. Earlier, this logic of map reduce paradigm as well as this logic of task tracker job tracker both was packed in a map reduce one. Okay, there is a single module. In Hadoop 2.0, they split MapReduce into two portions. MapReduce, pure MapReduce, and this job tracker and task tracker kind of basics, basically a network communication between you are saying that execute anything instead of just MapReduce logic. So MapReduce is just a programming paradigm. And so instead of just tying the whole Hadoop to MapReduce logic, Hadoop 2.0 said that let's just split this whole MapReduce component into two portions. One is execution unit, other is MapReduce paradigm. Execution unit can execute any paradigm, while MapReduce unit will use this execution unit called yarn to run your programs. Okay, an execution unit contains all sorts of resource management. Okay, and yarn means yet another resource negotiator. Resource negotiator means it will negotiate with all the task trackers about the resources. Okay, it will try to figure out best possible way to use your cluster, and use your computers, and that is why it is called yarn. So basically, it is a modularization of MapReduce framework, so that instead of just supporting one form of processing, which was MapReduce form of processing, there are other data processings which are possible as of today. And as a result of this modularization, breaking it into two parts, one is the resource management part of it, getting a task executed on multiple nodes and all that sort of management of the resources, and this particular portion yarn can be is being used by many kind of modules, not only MapReduce. Okay, such as Apache Spark, which is now a competitor to MapReduce, is using yarn, and there are other databases, other systems which have started using yarn for their execution in the network. Okay, so that is the difference between Hadoop 1.0 or Hadoop 2.0 and what is yarn. But for the end users, those who are using Hadoop, they don't have to worry too much about the yarn, because this is completely invisible to the end user. Okay, unless and until you are building a tool like MapReduce, or you're building a tool like Apache Spark, who has to understand and talk to yarn, you do not have to worry about it. All right, and in case you have you know you have already in case you have already written MapReduce in Hadoop 1.0, the same code is available in Hadoop 2.0. Same code will run on Hadoop 2.0's MapReduce. Basically, you just have to recompile, and that's all you have to do. You don't have to worry about rebuild, rewriting your MapReduce logic. So it was the Hadoop 1.0 to Hadoop 2.0 was basically a modularization step, where it broke the MapReduce component into two portions. And now on the similar line, like you have got MapReduce, there is something called Tez, there is online HBase, there are streaming systems like Apache Storm. Then there is a graph database like Giraffe, GIRAPH, which helps you doing a lot of uh, you know processing. And then there is something called in memory a processor like Apache Spark, which partly they're in memory, and partly it is on the disk. We'll be talking about HBase. We'll talk briefly about Storm, and we'll talk briefly about Giraffe. No, we'll not talk about Giraffe. We'll talk about Spark. We'll talk about, yeah, we'll not talk about others. right? So now as you can see that because of yarn there are so many systems being developed, and so many systems are being able to reuse the reuse this resource management module internally. All right. Okay. So this was the benefit of using yarn: support for workload other than MapReduce, scalability. Okay. And compatibility, they kept compatibility with the old MapReduce, they did not break that. And it improves the cluster utilization a bit more better than the previous one, and it became agile. All right. So there are various nodes. I mean, the same terminology, job tracker, task tracker, is broken into these nodes. All right. But it is safe to stick to the notion of job tracker, task tracker rather than getting confused here, because these terminologies are still well accepted. Okay. So we'll mostly stick to job tracker, task tracker, because they are very well accepted as of today also. Okay. So that's pretty much about yarn. It is just basically showing how the yarn is functioning, right? But do not worry about much. Okay. Now, on your, were you able to, you know, open the, if you go to my courses under this particular course page, were you able to look at the quiz, and were you able to look at the installation instructions? So for using Hadoop, there are two ways to do. First one is logging into our cluster, all right? And second is using your own desktop. Okay. Logging into our cluster, you can log into any of these nodes: Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4, or Hadoop 5. And you can use the same login and password, student and systies. All right. Student and systies. Okay. Second part is there is something called Ambari. Ambari is basically our administration console. Okay. You can use this student's account. Right now I'm logged in from another login. And from here you can basically see the what is my state of the cluster. So in your organization, in case you are planning to set up an Hadoop, you should basically set up Ambari server node and agent node on various computers, and then using Ambari server you can actually propagate very easily the Hadoop to all the nodes. Okay. So I'm not going to go into the details of that one right now, but in case you guys want, I can take a extra session for installation alone. Okay. I can take up a extra session in case you guys want me to go over the actual installation of the Hadoop. Alright. So here using Ambari, which is on 8080 port, it shows you the details about what is the status of our server. Let's take a case. Now we have got HDFS. It has got a name node. Name node is up and live. It has got secondary name node that is also up and live. And then it has got four data nodes. All four of them are live. Now let's have a look at the name node. So name node is basically running on Hadoop 1. Okay. While these four data nodes are actually on all the nodes: Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4. Dot no big data. All right. So that is That is we have installed these four data nodes, and if you see here, if you see here, the HDFS disk usage is 38%. Okay, and here data nodes, these many data nodes are live, and you can see the complete details. All right, and also you can go into host, and then you can see that these are the host, and on each host what all services are installed. Okay, so you can see clearly that what all components are stored. So data node is there, there is HBase client, there is HBase master, there is pig, Hadoop, Taze client is there, Yarn client is there, all right, and Zookeeper is there. So all of it is basically running on our cluster, and each individual node shows what all is there. If you have attended my first session, there I discussed very briefly about each of these components, except for Gangalia and Nagios, whose main job is for backup and monitoring. These both Gangalia and Nagios is basically monitoring of your system, right? Does it make sense to you? So this is just admin console which shows you the state. In case I want to restart some node, I can quickly restart a node saying, you know, started, restart, stop, or whatever I want to do. But don't fiddle with it. All right. Just keep it view only. Now, similarly, now that was Ambari where it was a admin console to you. Right now here there is something called hue. Hue is basically a web console to do lots of things. Now you saw we talked about data nodes containing these files, that file, but HDFS is actually keeping all of the data distributed across. Okay, let's take a case of, say we are looking at the sensor data. Okay, these are the the data of my older projects which were running. Okay, it has been deleted. All right, so okay, so most of this data is basically from the other sessions. Some people are doing their projects, so do not fiddle with their system. Okay, so I'm just taking an example of showing you what data and why. So say for example, there is this 17 GB file. Okay, there is a 17 GB file, and this file is actually distributed across the network. And if you see in the Ambari, okay, if you see in the Ambari, it is basically distributed onto the, okay, I mean, it'll be a little difficult to show you that what is going on with all of this. Let me just try to give you an idea. Now you can see that this node is how much? 12 GB, 12 GB used. This node is 13 GB. This node is 12 GB, and this node is, uh, you know, 17 GB used. Okay, so which means that this file is actually stored on multiple nodes. If you go into that folder where the data node is going to store the actual files, each small chunk, the data is completely meaningless, and small portions are kept in each file. Okay, so there are so many files you will find in that each data node containing 64 MB each. The chunk size the chunk size of the HDFS by default is 64 MB, and in case of Cloudera it is 128 MB. Okay, so that's pretty much about your file browser. Similar to file browser, you have these command line for pig, where you can write your pig command and execute it. All right. Similarly, do not fiddle with other users, because most of other candidates are also trying to execute their job. So do not delete anybody's work. Just create your own, and then in case you want to read somebody's code, read it. I have not created individual's account just because I want everybody to see each other's work. Okay, and so that you can see that how to do this, how to do that, because in case of programming, you learn by examples. You look at the various things and then you learn by examples. So this is h-based table. Okay, in case you want to see the data what is there in various tables, you can use at these things. So all of those components which I discussed in the first session can be used from the browser itself without installing, without doing any installation right away. All right. So that is another way. Now the other way would be that this was web version. The other way would be you SSH onto any of these nodes. And in case you don't have SSH on Windows, you can use PuTTY to install. All right. You can use PuTTY to do the you install PuTTY and connect PuTTY to this server and give these login and password. All right. So that's pretty much about the cluster. Now, in case you want to install a local version of the whole stack, which we have just discussed, so you can install the whole stack onto your local machine by downloading the virtual machine from. First, install a VirtualBox from virtualbox.org. After that, go to Hottenworks virtual machine and from the download page, download the Hadoop virtual machine from there. Okay. Now, once that is installed, you can do this. Okay. You can find out the IP address of the virtual machine you have just installed and then open it in the browser, or you can start using it the way we have been using. I was explaining about how to use our administration console. Okay, you can basically whatever we have installed on the server is basically Ambari and Hue. Okay, and same thing is comes in the Hottenworks also. They also pack Ambari installed virtual machine where all of these services like data node, name node, and H-based server, H-catalog server, all of these servers are basically running on the same virtual machine. Okay, so it is not that big a deal to actually install a virtual machine. Download this VirtualBox first, and then download the actual virtual machine. Open the downloaded virtual machine in the VirtualBox, and that's pretty much it. All right. So that's about installation, mostly the installation. Okay. And my philosophy during the whole class is going to be I'll go a little slower. In case I'm going a little bit faster and you don't like it, you just stop me then and there so that I become a little bit slower. All right. So even if the syllabus does not complete in 10 sessions, I will let it overflow to the 11th session, but I will not hurry up and make it troublesome for some people. All right. So Karthik's question is that how does Hortonworks Hadoop virtual machine differs from Cloudera's? So basically the difference is, I mean, from your perspective, the one which comes from Cloudera takes lot of disk space. Okay, and it keeps on expanding. The moment you do a little bit of operations, it starts expanding suddenly. So it has become little fat. Okay, from the technical perspective, they have their own Cloudera manager to install things, while Hortonworks has their Ambari, open source Ambari, which we have just described as a interface. Ambari is basically a tool which lets you install all these machines without actually going to any of the nodes. Okay, say for example here I was describing to you in Ambari, I can actually go to services node, and then I can say that on the services page, you can see this here. What I can do is I can say move. If I don't like name node on this machine, I can say move, and it will ask me that are you sure, and then it will ask me where do you want to move it to. All right. So you do not have to fiddle with anything. Okay. All you have to do is if you want to set up such kind of environment, on one node you install Ambari server, on other nodes you install on one node you install Ambari server, and all other nodes you install Ambari agent. Okay. And wherever you have installed Ambari server, that's where you will be accessing it like this. Okay. And then you will say host and say add host. Okay. If you want to add more host into the network, you can say actions add new host. So first you have to install Ambali agent on that, and then give those host name, and it will install all the components which you want to install on that. Okay. It is as simple as that. So in case you are planning to install, I found it far easier. So I was actually struggling with Cloudera Manager. Cloudera Manager was trying to do the same thing as Ambari, but Cloudera Manager was closed source, and I found it little clumsy than the this one. I tried Cloudera Manager couple of times, but it did not work. We were using Cloudera Manager earlier on these our cluster. All right. So this is about the Karthik's question. Was I able to answer, Karthik? Now let's. So now if you I'll just show you that how do I connect. So I say SSH and then Hadoop, and then I say no, not that. I say SSH student at Hadoop, and then I say nobigdata.com. And it'll ask you for password, and then password is visible in the installation document. All right. And here you can see that there is this folder. Always make your own folder with your own name, and then put your data in that folder. Okay. And now I demonstrated you that there was HDFS using web UI. We went to one folder. Inside that folder there were some data, and there was 17 GB file. All right. Similar thing you can also do from here. You say Hadoop file fs minus ls. All right. So it shows you that these are the folders in the Hadoop file system. These are not the folders on the local file system. Okay. Like for example, let's check whether is there a sensor file localhost? No, it is only in the HDFS. Now let's just go to again the same data folder which I demonstrated you earlier, and also on the HDFS itself you should create your own folder. Like as an example, I say Hadoop. I think you will find doing all of these file operations better from Hue. Okay, Hadoop one, and then you say 8000. Okay, so on HDFS also always create your own folder and then work upon that one. Okay, the way all other users have created their own folders, you should also create your own folder, and whatever data you want to keep in, you should keep in that folder. All right, so that's and if you are really interested in knowing Hadoop command line, so there is a Hadoop command line which is basically a client. It has got most important function over here is Hadoop FS. Okay, Hadoop FS basically allow you to manipulate HDFS. Okay, and here you have all sorts of command. If you just type Hadoop FS, it shows you all sorts of commands which are supported. In case you are coming from a Unix background, you can you quickly correlate these basic commands. Or even if you are coming from DOS, you will be able to see all of these, understand all of these commands. So this is basically to manipulate HDFS. Say here I want to make directory, and I say SGG. Okay, and now locally I have say a small a file. Okay, and let me just take a small file, and say I have got one small file called abc123 abc.txt, and I can copy that one quickly. I say Hadoop and then fs, and I say copy from local, and I give the local file name whatever is there, and then I say my remote folder name. Okay, now it will copy this file from local to the directory which I just created using make directory, and I say Hadoop fs minus ls sgg, and it will show me whether that file is there or not. So you can see that file is there. Now let me do a cat. What is there in this file? abc.txt. Alright, so this is some portion of the file. Now similarly you can you know uh, go to the file system. Here I have created a folder over here. And is there a refresh? No. So there is my folder which I just created. This is the file which I just uploaded. Okay, when I'm uploading from local Hadoop 1.no big data to the HDFS running on our cluster. Okay, that's pretty much. So similarly, you have got this is fine, and then when you want to run a MapReduce, all you do is basically Hadoop jar, and then you can see you will put your jar file name, my.jar, if you are coming from Java background. Then whatever is your entry point in that whole zip file. Jar is basically a zip file containing all your binaries. Okay, and in that one you can give the name of your class containing the entry point, or containing the MapReduce jobs entry point, and then you can provide all the argument which your class is expecting. So that is how you schedule a particular MapReduce job onto the cluster. Okay, and now similarly we have got pig everywhere. Okay, so if you have to run pig, you can run a pig like command, and then run all the pig commands whatever are given. Okay, and similarly we have got hive here. You can use hive. So when we will go into each class, like when we start describing what is pig, what is hive, then you can start using all of these. Okay, okay, great. This was just to give you a demonstration. So yeah, this we have discussed already. And on Windows you use putty to SSH, and when you want to copy the files to our servers, there are two ways. So first way is that okay first way is that, say you have got file on your desktop. Now you want to upload it into the HDFS running on our server. Okay, now first, either easiest way in that case is that you use this interface. Okay, you use these interface here and upload the data. After you create your folder here, upload the data, or you use WinCP or SCP command to copy the data first here onto the remote Hadoop one, and then from there you use Hadoop and Hadoop, you say fs and say move to move from local. Okay, this will move a local file available in this Unix, which is Hadoop 1, to HDFS. Okay, okay. Now that is the general strategy. So in case, as a general thumb rule, in case your file is below 4 GB or below 3 GB, within say 3 to 4 GB, up to 3 to 4 GB, then uploading using web interface is better because it's a single step process. You just directly upload it to HDFS without first putting it somewhere else and then doing it. So that is better generally. And in case you see, when you have an organization and you have a Hadoop cluster somewhere on the remote. So the way people do is they install Hadoop client on the machine containing the data, and then tell the Hadoop client where is your cluster, and that Hadoop client will basically, Hadoop client is this Hadoop, this command line. Okay, this knows based on its configuration file which we have mentioned, that where is. So Hadoop client knows we have configured Hadoop client to, if you see user, so under that one, so where is my, okay. Now, basically in the vim etc and then Hadoop and then under conf and then you have sdfs site.xml, it shows you that. Okay, so this is my data node address, which is local. Okay, and it knows that where is the data node, which is the name node, and all of those details are there. You can see the name node address. It shows you the name node address. All right. So basically, we have already configured using HDFS site that where is our remote host is available, and we upload to using this one. So when you are basically moving a lot of data to a cluster, the standard way of doing it is either using a Hadoop client on that machine and then telling that Hadoop client that our cluster or name node is lying somewhere in the remote. We tell the IP address or the domain name of that one and then start moving it. Okay, because that is very, 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 very cost effective. Because if you use Hadoop client effectively like dist copy, it is very, very fast and powerful. So that is pretty much about. So I've described you how to do it. Okay. So this is how we ran a command, and then we have got pig where we are loading some file and then executing it. So you should try out all of these commands on the server. Okay. In this step, we have taken a big text file and uploaded some on the network or into the HDFS. Then we used a pig command. This is the pig command. So first we execute pig command. Then we say we load a particular file as this one and then dump that particular file. Similarly in Hive, you can quickly test whether Hive is working or not by running a similar command. Okay, all right. Now, basically, I would like to take you through a MapReduce job, and then we will start with our process of executing. All right. Now, so in this particular job, all we are trying to do is, okay. So since you guys are not asking question, I'm wondering, have you slept off? Hi, is everybody with me or have I lost you? Because you guys are not asking anything. Akhilesh, Ishwar, Jagannath, Karthik, Meenal, Prasanna. So are you guys with me or do you have any questions still here? Okay, great. Ish- Ishwar is awake. Excellent. Akhilesh is awake. Okay. If you are storing 2 GB file as small, what will be its size? So effective size will be little bigger because I mean actual size on the disk is going to be similar, just that there will be a storage of metadata here and there. Okay, like name node will have extra data. Similarly, when you are making so many entries in the file system, the fat file allocation table will take up a space. So the actual size of the files will remain. If you sum up the actual size of only the files, then it will also have few bytes of the header information. Okay, but actual data will remain same. There is no extra space allocated along with the actual file. Okay, does it make sense to you? No, Karthik? So basically, unlike the way, say for example, you must have studied database somewhere. When you add a record to a table, in the actual file, there's a lot of space left for future planning. Okay, vacant space left between the file or the record so that more records can be added. That's not true in case of HDFS. HDFS is just like taking a file, splitting it using split command, and then putting it on multiple nodes. It's as simple as that. Okay. Now, what happened to this guy? Okay, got it. Session. Okay. So, great. All right. Now this is our file. Now let's go into student. Under student, this particular example is available in something a folder called word count. Can you see a word count or have people deleted it? Mm-hmm. Mm-hmm. Have people. Okay. Okay. Okay, it's under Asgiri actually. Okay, we have Asgiri and all right. Okay, now just to give you a demonstration of word count example, that word count example is by default available in almost all the MapReduce examples. Okay. Huh. Actually, okay, good. Now, okay, so I have already created uh, MapReduce classes. All right, I've already created MapReduce classes, and I had created a jar already called training2.jar over here. All right. So just to give you a demonstrator, I do not want to, scare you away with with all sorts of details about Java classes right now. But so when you have written your MapReduce into using your Java code, and .jar for those who are coming from .NET background is similar to saying dot uh, tar.zip, or maybe in the terms of Windows speak, it is similar to also analogous to .dll, where it contains all the library functions, everything inside a single file. All right, it combines everything into a single file. So here you can run it like this. Okay, now what is my think I'll just load my Eclipse. Okay, so let me just take a case of where is my file. So the way I'm executing it using Hadoop jar and my training2.jar and then my stub driver, and then I can put put the name of the files. All right. Now my input file is word count and then input. So I can here give the input directory as is, and it will find out what all files are there in that folder. So this task basically is a very simple task, which is a hello world, in which it will take up the all the words from this folder, and basically this file, which is 6.2 MB. It will go through each word and prepare a statistics of which word has come how many times. All right. So I will rather store in my own folder. So basically all I'm trying to demonstrate to you, you have written all of your code in this jar file, or somebody has written the code for you and prepared this jar file, and you want to run their library onto your Hadoop cluster. So all you do is Hadoop jar and then that uh, actual file name, right? And then the entry point, which will be the person who has written this jar will tell you that what is the class name, and then you specify the whatever argument this program requires. Okay, this program requires, in my case, it is requiring input directory, output directory. So it will take the file from input directory, compute statistics, and then save it in the output directory. Okay, basically a it is simply preparing a word count on all of these, and this is how when you press enter, it is going to run it as a MapReduce job in the network. All right, so you can see that that this is the status. Also, this is the way you can see what is going on with this one. All right. Okay, as you can see here, there is some error. It is saying that it has failed. The class stub class is not found. All right. So probably the code is not written properly. Okay. So failed map task is 4, launch map task is this much, and okay. So probably this file is invalid. Maybe we'll need to see that. Alright, we'll take it up again when we describe to you how to write MapReduce in detail. Alright, when we are talking about how to write MapReduce in Java. So all I was trying to demonstrate to you is that you have written your code here, and then you're trying to execute onto a network. This is the exact command you can use. So whatever jar is given to you, you give entry point of that one, and then you specify the command line argument. And you can also monitor the what is going on. Here it is showing that all of the maps have failed. Okay, so we'll go into these details. I was just trying to show you that these are the kind of commands we'll be using. So get yourself familiar with Hadoop command. Okay, and now let's move on. Let me take a couple of notes. Now, in the second half, we are going to discuss about MapReduce, and once we are familiar with MapReduce, then we will move on to any other things. Okay. So just before we take a break, of say 10 minutes, you should here is a question for you. Okay, if you have a plain text file of all the Lord of the Rings book, how would you find the frequencies of the words? Okay, think about it, think about it, and we will talk about it after the break. Okay, so let's take a break of say 10 minutes. So after the break, we will be discussing about what is MapReduce and basically how do you convert most of the problems into a MapReduce problem. Okay. So we'll start from a very, very basic problem, and this is the first problem. All right. Let's meet at let's meet at let's meet at 10:14 p.m. IST. Okay, in 10 minutes. All right. Are you guys there? Hi guys, I'm back. Are you guys back? Should we start? So great. So what did you think about this problem which we talked about just now? So if you have a plain text file, a huge file such as all the Lord of the Rings book combined together, and you have to count how many what is the frequency of each word. Say a word is repeated 100 times, so it should show that word and 100. Okay. So, if you have to compute the frequencies of the word which has occurred in a file, how would you do it? So quick, it's a question to you, not, I mean, I'm actually waiting for your answers. Just feel free to say how, if you are asked this problem, say you have got a big text file, say maybe this file is around 100 MB big, and you have to find out the frequencies of the words in this 100 MB file. What will you do? Is the question clear? Okay. Maintain a hash map where word is the key. Excellent. And maintain a hash map where word is a key and the values as count, and keep an increasing count. Perfect. 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 So anybody else? So this map will be in the memory. All right. We'll store all words in a sorted list and count. Excellent. So what Akhlesh's approach is, first, uh, you know, basically all we need to do is first break down the file into a list of words, then sort this list so that we have same words together, and then we count the numbers. Is it a case? Is that what you're saying? Because in case you have sorted the file, all the words, same word will come together. And then if you start from the top, you go down to the bottom. The moment you encounter a different word, you print out the number. In case you have not encountered a different word, it's the same word as the previous one, you keep on increasing the count. Right. Great, great. So Prasanna and Akhilesh is similar, and Karthik is using a hash map in memory. Great, great. So these are good approach. Any other approach in real life, in practical, what will you do? Say this is the thing you have to do for your job in your day in day out, and you are asked, look, we have got lot of text from the user, and all we want is the frequencies of the words every now and then. What will you do? Will you use a database? Will you use something? Any idea will do. If you do not think about it as a algorithm problem. So I mean, feel free to. I want more ideas on how to do this. So we have got two approaches. One is hash map, which is great. Then another one is a sort one, and that's also a wonderful approach. Both of these approaches have got their pros and cons. We'll talk about those in detail. And What are the other approaches you think about? So these are very, very basic questions I'm asking, because basic in the terms of the computer science part, it will make you force you to ask various kind of questions. And when you're designing your systems tomorrow, you should be able to formulate similar questions. Excellent. So any other approach you have in mind in the real life project, if you have some other approach? So So this first approach is similar to Achilles's approach. Create a frequency hash table. As we walk through the file, we pick up a word and check in the frequency table whether we have encountered that word earlier or not. In case we have encountered that word earlier, we increase the frequency, increase the count by one. In case Excellent. So Ishwar is saying that the RAM size matters here. Great, great. So first approach is create a frequency table, then for each word, and then you keep on doing it. Once you are done, then that's it. So Ishwar is saying the biggest problem in this approach is the RAM. Any other problem do you foresee? But drawback is we have to take data to program, which makes this computational slower. Very good, very good. Okay. So basically, we saw two problems with this. First, in case your file is located in the network, right? So you will read word by word from the network and then do this computation on this node, unless you are able to send this code to the node where the file is located and run it then and there. Good. So we have got two problems with it. First one is basically the RAM, and second one is that. Great. Excellent. So now, since RAM is the problem, what will you do? Okay, RAM is the problem because hash table is close to four times the actual data. In case of Python, it is actually more than four. In case of Java, it is similar, maybe three times of the actual number of records. So what do you do? Okay, what do you do in this case? If your say RAM is 1 GB and say your file is also 1 GB, so it would require a hash table of around 3 GB and do it. So this first approach has got a problem with respect to RAM size. Okay. Okay. Now second approach is that you know this is like a practical approach which people come up with. Break the book into one word per line. Break the book into one word per line. All right. And so this in this approach where you broke all of the books in one word per line and then took this whole data and put it in the database. Okay. Now you have got a table with a single column called word, and then you say select word and count star from a table and say group by word. This will give you the counts of each words. Okay. Most of the RAM, the sorting of the data will be done by the database. Even if the data is not fitting into RAM, it will be able to do it. All right. Now this is the second approach. Now, in case of third approach, this first approach was the first one which we do. Either you know take the data and put it into a hash table, and then for each word we do the run prepare a frequency table and then move ahead. Now the problem with the first approach was that in case RAM size grows big, what happens? In case we are not able to store the data, then what do we do? Now most of the SQL databases are well tuned to handle the bigger data than the data which fits in the RAM, and therefore this code will work fine. Now third approach in the game is, I mean, there could be hundreds of approaches. I've just taken few approaches in the real life, and here the third approach is using a Unix command line. All right, where you first uh, you know concatenate all the files which you want to sort, then replace. Here, how many of you know regular expressions? Very quickly, how many of you know regular expressions? Okay. Okay, great. Great. Basics are only required, so nothing to worry. So regular expressions are like those wildcard character matches which we read in the DOS, like dir star dot star, dir star dot bat, similar to those kind of where we want to with the match a pattern. So it's a that one. So here I'm saying that this is how you define a regex. Here I'm saying that space or tab any number of times, plus means any number of times. Okay, here space or tab, when I say square bracket, it is all the character ranges. So space or tab any number of times, at least once, should be replace. This is like saying control F in your text editor. Control F, replace this with this, and this is any space which you encounter, and replace that space with the you know the blank space or white space, you call it. White space can be in the form of space, normal space, or in space of in the form of tab, and you replace that white space with new line character, which means all the words will come in a one line per word, one word per line. So okay, and before I talk about this command, how many of you actually know the Unix pipeline? This is little, I'm moving a little too fast. So when we talk about in Unix, basically it is similar to Windows. Windows also has pipeline, whereby the output of one program becomes the input of another program. When we put a pipe between one program, so here this is one program, which is basically concatenating all these files data to the output. And that whole data is being fed, it is being fed to next command, which is SCD. Is, you can think of this particular command as control F option, whereby as soon as it will encounter any space in the input which is coming to SCD, it will replace that space with a new line. Okay, now whatever comes out of this replacement, which means one word per line, that will be given to sort. Sort will basically sort this file. Okay, sort this file, and using a memory of 2 giga, 2 GB. Okay, using a memory at most of 2 GB, and then say unique. unique minus C, and that's all. All right. So here the magic is mostly done by sort and the unique. And these guys just prepared the data, which means one word per line. That's all they did. Here it took that all the lines and ordered those lines by alphabetically, and then fed it to unique. Unique basically counts the words only if the words are ordered already. Therefore, we had to use sort command. And sort command is beautiful in the sense that you can specify how much memory can you use. Okay, this is very important step. So this is the pipeline where this output of cat went to SCD, output of SCD went to sort, output of sort went to unique, right? So how many of you understood? I did not understand this. This is a very important aspect. So all of you understood this? Okay. Okay. It's basically all I'm trying to say is that using a command line, all I've done is taken all the file's content, converted that file such that it should be one word per line, and then used a command called sort, and in the sort I said should be sort 2 GB. Okay, now Karthik's question is that when what happens when data size grows bigger than RAM. So let me explain this. So when the cat does not require any RAM, because all it does is takes the input, gives it to output, right? Now SCD doesn't require too much of RAM. It won't load anything into RAM except for few words or maybe one line at a time at most. But sort command for sorting needs to load a lot of data into memory. Okay, sort command need to load whole of the data into the memory. And when we say sort minus as 2G, all it does is it converts the input file into chunks of 2 GB files and then sort them individually and then merge it finally. Alright, that is what is done by sort minus as command. Right? So basically, how much ever data you want to sort at one go should be loaded into the memory. Therefore, what it does is it divides the data into smaller chunks and then sort them individually and then merge them together using the sort command internally. Right? It's called disk sort. There is an algorithm called disk sort. This is what it does. Right? So it doesn't go beyond 2 GB. It doesn't take the beyond 2 GB because we have said that our use only 2 GB of the RAM. Okay, and in case your RAM is smaller, say 1 GB, you will say 1 GB here. Right? So this is how the sort functions and gives you this. So this basically solves your problem similar to what SQL did. Okay. SQL also does a disk sorting and most of the SQLs are pretty good with disk sorting. Now, how many of you think, because approach number 2 and approach number 3 are almost similar. One we are using Unix, other we are using SQL. All right. So what exactly do you think are the problems with approach number 2 and approach number 3? Anyone? Performance, perfect. Any other? Performance in the sense what? what are the reasons for degradation of performance? Mm-hmm. Mm-hmm. Okay. So slower execution is one problem. Why? In approach 3, there are lot of operations required. Lot of operations. In approach 2 requires some interface to load data in SQL. Yes. Okay. So you are saying, Akhilesh is saying that basically the approach is a little bit of, cumbersome, right? Ishwar is saying that it is a little bit cumbersome, and okay. Approach 3, sort and merge, would take a lot of time, which include loading, unloading of the file in memory. Perfect. Perfect. Right. Right. So, yes. So basically, whenever you read a file from the file system and doing all of these sort of things, first, when you are reading from the disk, when you read from the disk read takes a lot of time. All right. And second is once you have because if the bigger the file, the more data you have to read from the disk, and or you'll have to create more number of chunks to so that because it fits into the RAM, and therefore your disk is getting becoming bottleneck because read speed is taking time. Right. Right. So here is couple of things. The moment the data starts going beyond the RAM, the time taken starts increasing, and the following things become bottleneck. First, RAM became bottleneck. That is why we used sort command with a special parameter saying use only this memory. Then network speed. If your file is located, which already somebody Akhilesh I think mentioned already that if you are reading it from the network, it is going to take time. Third, disk space or disk speed might become a bottleneck after some time because when you split a file, it is going to create a copy of this one, and that is going to take your disk space. Similar disk speed. At what rate are you able to read from the disk will be the deciding factor. How much time does it take to process the data? And then finally CPU. All right. Now, now what should we do? What should we do? Can we utilize multiple machine to count the words for you? If you have say few GB of data, say 30 GB of data, okay, or say 15 GB of data, it will make a lot of business sense to use multiple machines, right? And how would you use these multiple machines? That is one big question which people ask, right? So first command is that you divide your input file into small chunks, right? So and say you have got two machines and you have got 4 GB of data to be sorted. So what you'll do is you'll create two pieces each of 2 GB data and send it to machine 1 and machine 2. Or in case your file is located in the network, you will just say you will just split this file into two portions and give first file into machine 1, second file give it to machine 2. right? And let both these machine use the previously mentioned algo, either of those algorithms. The first one, let's say hash map approach, let them use hash map, okay, and do the computation for you and give you the results back. Okay, but while you are returning the results back, make sure that you return the results such that the keys, the words are in the increasing order or decreasing order. So your keys, hash map, your keys should be ordered. Okay, I will talk about it a little later. Why? Now, once that is done, you merge these results. Like, say you had two files. First is just containing sa re re. The second one ga ga re. You basically splitted your file into two files. First one containing only these three words. Second containing only these three words. Of course, this is just for oversimplification of the problem. Okay, here it will be like a billion strings this side instead of three strings. Okay, here I've just shown you, for example, like three words I'm passing, but there will be like billion words I'm passing here. And in result it gives us this: re is 2, sa is 1, ga is 2, ga is 2, and re is 1. You can see that now these words are ordered: ga and re and sa. Now, merging a ordered list is very straightforward and can be done very quickly. Okay. And how do we do it in case of Unix? On machine 1 or machine 2, you can use the approach in the previous one to sort the data using sort command, or you can use a hash map, your own algorithm, and then you can use sort minus m to merge sorted list. Okay, sort minus m helps you merge the sorted lists, and that is what it is. Okay, and then you can do a unique minus c again. So that is, so this makes a very very simple use case. Basically, sort minus m does, when you merge two big lists which are already sorted, all you have to do is keep on reading both the files together and then keep on merging it. It's pretty straightforward. Okay, it's if you go through merge sort algorithm, so you can, if you are having difficulty in thinking in terms of file, you can think in terms of, there are two queues, and both the queues there are people standing in order, in their increasing order of their heights, and you have to merge these two queues such that they become a single ordered queue. Okay, a queue containing people who are standing in the increasing order of their heights. So that is very, yeah, it's easy to actually merge sorted list. So this is one approach which lots of people had been using for years. Okay, so we take a file, divide it into small chunks, send it to multiple machines, and then get the work done on each machine, and then return the results such that merging those results is very easy. Okay, this is the approach which we had been doing in 1990s, 1980s to do a parallel processing in the network. Okay, so did you understand this approach? Let me know in case you did not understand. I'll repeat it again. Akhilesh, Ishwar, Jagannath, Karthik, Meenal, Prasanna. So basically, we trying to divide our job onto multiple machines. And the way we are trying to divide our job, the current job at hand is finding the frequencies of words in a huge file. Are you there? You should ask a lot of questions, and I would basically, you know, either I'm really great at answering the questions, or I have completely confused you, and that is why you are not asking questions. So which one it is? Is it that I have confused you, or there's nothing to ask? Okay. So the whole, I mean, you should, I mean, w- you should be asking more questions, and feel free to ask the questions. Okay. In case, we are getting a little bit delayed, it is okay to get delayed. All right. Logically, it's clear, but not sure how to implement. Okay, Akhilesh, this is a very good point. And in case you want to try it out, let me know. I'll show it to you. And basically, we use sort command itself. There is a split command in Unix which can split files into small portions, and then you can use sort command on each portion, so it will create hundreds of files the moment you say split my big file into 1 MB each. And then what you do is use a sort command to sort each of these files. And then once you're done with it, use sort minus m, which will basically merge all of these chunks together. Okay, so that is the way you implement it. All right, so try sort minus m and sort command, and then try to see the magic. All right, if you have access, you can do that on Hadoop one. Create your own folder, put a file, put this big.txt, which is there in asgiri slash word count. All right, asgiri slash word count slash input, there is a file called big.txt which contain lot of text. Okay, try to do that. Great. If we run, okay, so great. Karthik's question is, if we run this on more machine, would it increase the performance? It will improve performance, Karthik, because first, now you got better. Now there are two disks, two hard disks, one on machine one, one on machine two. Both disks are reading the data at the same at now total pace at which you are reading the data from the disk is twice, right? Both the machines are doing parallelly. Now that data, because that data is generally the biggest time taker. Okay, after you have read this data, the next step is to do the sorting, or you do it both the things parallelly. First one is reading the data from the disk, and parallelly you keep on checking in your hash map. Okay, both of these things can be done parallelly by creating queues. So you read a chunk of the uh, you know say 10 MB 10 MB at a time, and then by the time you are reading 10 MB, let the the previously read data to be inserted into hash map, so you can do all of those magic. All right. So basically, what I'm trying to explain is that first bottleneck, the first portion which consumes lot of time is your reading from the disk. So that became twice. We got two machines, two hard disks, and both of them reading simultaneously. The second one is we got twice RAM, right? And then third one is that computation, the CPU, the CPU, we got two CPUs which are parallelly doing the job. So of course it will improve the performance. The only question when it may not be greatly performant is when your network is extremely slow and your file is located on one of the nodes, okay, on the same node. All right. So, and therefore, in only in those cases where file is located not located on machine 1 as well as machine 2, and there is a file transfer involved, and in only in those cases it will not be greatly at performance. So what other reason do you think will it will would be the reason, right? So your question is that if we add say one more machine, okay, instead of two we add one more machine, three, will it improve performance or not? If doesn't, then what do you think will be the reason? Okay, so the and your concern with respect to the file transfer, if it is that, is very genuine, and we will discuss it in detail. So this one is okay, right? Now third one is, here this actually the way we have done just now is called external sort. We sent it to multiple machine, or we split it the file into two portion. Both are called external sort because they involve similar step similar step of splitting and then merging, splitting, sorting, then merging. So whether over the network or using on the same node, it both is called external sort. So problem with external sort is, so this sort of thing actually works pretty good. Okay. So the problem with this one is that each requirement, whenever now I'm asking you to for word count problem, tomorrow I ask you for a simple problem like as simple as, how should I say, as simple as that, sort people by their surname instead of first name. Okay. Now every time for each of these small tasks, even though they are variant of the similar problem, you end up writing a lot of code. Okay. Problem with these external sort and these previous approaches is that you are doing the plumbing by yourself, splitting merging and all that sort of thing you're doing by yourself. And before that you're trying to convert your data related problem into various programming aspects, which is difficult to mostly, right? So basically, whenever you do this kind of thing, a lot of engineering is required. And also, since the file is not available on the same node, it will require time to transfer that data. Okay. So time is consumed in transport of the data. Plus, for each requirement, we would need a special purpose network oriented program, right? Now, to solve these two problems, okay, basically first one is transport of data is the problem in these approach which I just described. Second one is it requires a lot of engineering, right? And the so solution is using MapReduce, and because MapReduce will actually decrease the effort of these two. Okay. So before we move on, now can we do you have any questions at this point? Okay. Okay. So what exactly is MapReduce? Whenever we talk about Hadoop, we talk about MapReduce, right? So MapReduce is a programming paradigm, okay, to help you solve most of these big data problems, and specifically sorting intensive job. Sorting intensive job is most of the data crunching which happens is basically can be converted into sorting problems. Okay. So in case of MapReduce, you will write your code in map and reduce, two functions. Okay. Mapper, the map and reduce or mapper and reducer. With these, the map and mapper are being will be used interchangeably, so don't worry about, you know, no, don't get confused. Map and mapper, the way I'll be using will be the same thing, and reduce and reducer is the same thing. Okay. So whenever you are writing a map job, you will be printing out you will be printing out the key and value. Okay, now, and in the reducer, so you will be giving out key and value in the reducer. Given a lot of values for the same key, you will have to convert it into a single number. That is the job of a reducer. All right, now everything else in between is done by Hadoop for you. Okay, so Hadoop takes a file, gives a line by line to your mapper. Okay, now mapper takes this line and converts this line into key and value. And after it is done doing that, Hadoop takes up these key values given out by your mapper, and note that the mapper is being run a number of times. Okay, if the file is located on 100 machine, the mapper will be executed 100 times. Okay, and once that is done, or you can think of it this way, that if you have 100 lines in a file, the mapper will be executed 100 times. And the mapper, whatever code you write in the mapper, it has to give out your code, whatever you write in the mapper, will give out a key and a value. All right. So whenever you're designing a problem, you write these map reduce, which give out key and value. Map gives out key and value. Then Hadoop takes that key and value given out by the map, and then prepares a list of values for each key. Okay, for each key it prepares list of values, and those values are given to your reduce function. And now your reduce function can be average, can be something like a mean, or whatever it wants to do. It can sum up all the values, or it can do a comma separated and the list return the value. So it can do anything it wants to do with those values for a single key. So a reduce will be executed for each key. Reduce will be executed for each key. And all the values for the same key will be given out to the same reduce. And MapReduce is actually a big paradigm, and almost all the systems support it, such as MongoDB, CouchDB, and other systems. And mapper and reducer can be written in Java, Shell, Python, or any form of binary. Okay, so you do not have to worry about that I don't know Java, then I will not be writing MapReduce. Okay, it's more of a general programming paradigm where you convert your problem into functions called map and functions called reduce. Okay, those logical units. Now let me just walk you through the through what is going on with a map function. Okay, so let's take a case of a map. So let me just see. Okay, so here is what map reduce is. So say you have got a huge file and you want to do you do a word count problem, the problem which we have been struggling with for some time now. So you are trying to solve this problem of word count. So I mean, in your map function, you will write for each word or print word as the actual key, and one as the numeral one as the value. Okay, that's all you print. Okay, say your file is containing sa re saga. So this code which you have written in your map function will go through each word. Say for example, first it will pick up sa and print out sa space 1, then re, then re space 1, and so on. Okay, now your map has converted each line into key value pairs. Okay, now Hadoop, or you can say map reduce of Hadoop, will take up this output and prepare a list of key and values. So you said your key is something, value is 1. All it did was it brought out all the values for a key together, right? Do you see? Sa has got two ones. Okay, so that's all it will do. Okay, whatever key you put in here will appear only once, and all the values for the key are combined together to form an array. This is an array. Okay, now on each of this key and the array of the values, your reduce function, whatever function you write in the reduce, will be executed. Here we have written reduce function which takes a word and a frequency array, right? So Hadoop will call your reduce function with these two parameters, word and an array. So ga and 1 will be passed here, ray and 1 will be passed to your reduce function, and so on. And then this will return whatever you wish to do. Here in this particular case, all it did was it summed up, it did a summation of these numbers, and hence it gave ga1, ray1 and sa2. Okay, had we been doing average here, then all of these values would have been 1. Okay, because 1 plus 1 divided by 2. All right, now, right, any questions on this? So whenever you try to solve problem, you convert your problem into a map and reduce functions. So here the way we have done is our map is giving out word for space 1, and our reduce is just summing up all the values for a key. That's all. Okay. Does it make sense to you? Akhilesh, Ishwar, Jagannath, Karthik, Meenal, Prasanna. So if you have any questions at this moment, just ask me, because I think that I'm able to explain. Maybe I'm not able to explain couple of things. Okay, so please feel free to ask. Okay, unlike our traditional classes where we don't ask questions, please ask more and more questions. Right. So these map and reduce functionality is provided by the Hadoop, and hence why we we need to write our own binaries. Very good question. So let me just take a step back. So map and reduce are the functions which you will have to be writing. Okay, which you will have to be writing. The code inside map and code inside reduce is your job. And then once you are done writing these code, you hand it over to MapReduce of Hadoop, and that guy is going to execute your MapReduce. And first it will take up your map, pass line by line to your map function. Whatever your map function is returning as output, it will take that, and it will take the output of all of your map functions, how many times it is executed on each line, and once that is done, it will sort the output, because your output of all the map functions is key and value. So it will sort all the values onto keys, and then combine all the values together for a single key, same key. Okay, and that's it. Was I able to explain? And thereby you will have to write MapReduce. Okay, now let me take another analogy. So MapReduce is more like your group by of SQL, right? So group by statement comprises of two portions. First is selecting a word from a table and then saying group by word. Okay. So we are saying please group by this table on word. Okay. Meaning, I mean that is what we do, right? So how many of you know this syntax from SQL? Select word, count star from table, group by word. Who doesn't know this? Okay. So, are I mean, are you all comfortable with this kind of SQL syntax? Great, great. So all of us know this kind of a syntax. So basically, if you see here, we are saying that take my input data, group it by this particular column value, and once you are done with grouping, execute count star or whatever aggregation function you do. Okay. So MapReduce just took this group by syntax to another level. All it says is that you can define a very custom key, not only the column value, but it can be inverse of the column value, it can be capital form of the column value, or whatever you want to do. Okay. So group by, in group by, when we say group by this particular value, all it does is take that one and then take all the other values other than that key, and combine those together for that particular value. Okay. And once it has combined together, it executes this aggregation function. Now this function is equivalent to your reduce function. Okay. So your reduce function can have very complex operation. It can be your custom one. It can be like, maybe, you want to do a root mean square value. Okay. Which root mean square value is like take under root of summation of all the squares of all the values. Okay. So instead of just doing count star, so it can be anything, it can be very complex. Even here you are limited by what does SQL provide to you. Okay. There, in case of MapReduce paradigm, reduce function is a custom your code. It can be in Java, it can be a binary, it can be anything. So you are not limited by various functions provided by some language. You can do anything you wish to do with these values. Okay. So say for example, if you just want to, you know do a sort of some sort of magic, mm, say you want to prepare a CSV out of this, and that you can write your own function, reduce function, right? So MapReduce provides you this functionality of preparing key value pairs, which means ability to group the data by a particular key using using your programming language, not only the query language. Okay. So these two sentence, select word from a table, is equivalent to map, while this is equivalent to aggregate. Okay. This, because group by statement comprises of two parts. One is group my data by this key, and once you have grouped, do this sort of operation on the grouped values. Okay. So these are the two phases, and these are very close to what is my MapReduce. So you will have to write your code to define how do you want to prepare key value, such that system can by default sort it by the key, that particular key. Okay. Is it clear, the MapReduce one? I think I've jumped a little ahead. right? Let me just take a step back and go through in details. Okay, here it was very simple, a single step where we have taken a file, map was run, and whatever output came in, Hadoop sorted those keys and brought all the values together and into an array. And once that is done, reduce function is executed on each of these, and whatever reduce function returns, reduce it, this is your code. Okay, this is what you will be writing, this portion and this portion. Okay, and rest of the in between is being done by Hadoop themselves. So from here you have taken to here using a map and reduce. Okay, and this dashed line represents what Hadoop did in between. Your map function created this list. Hadoop took this list key value pairs and converted into sorted it, remember, sorted it by key, and brought all the values together, and then reduce your function did a summation. Okay, this is your function, you can do whatever you want. If you want to do root mean square value, you want to concatenate by comma, you want to concatenate by dash, you want to do a ASCII sum, whatever you want to do you can do here as well as here, whatever you want to do. In case you want to break down this character by character, you want to make each character as the key, that it is absolutely up to you. Okay, it is absolutely up to you. Now, this was just to give you an example of the single machine. Let's say that we have two machines to do the task. What happens to your map and reduce? Okay. Say you have written your code map here and the same function is copied onto both the nodes. All right. Now, you have got two nodes, node 1, node 2. Node means a computer, a network node. Okay. So node 1 is containing this portion of the file, while remember we talked about data node and each node is containing a portion of the file. Say you have got two nodes, one containing this file, other containing this file, right? Node 1, node 2. Now you want to do a word count. Okay. So in the map, this is the code you wrote, right? This is the code you wrote. So whatever is the output of the map is sorted by the Hadoop sorting step. Similarly, here also happening the same thing, did the sorting. Then after the sorting has finished, there is a step where the data from both the sorting this is merged together and shuffled also. Shuffled in the sense that shuffled means again that, I mean, there was a merge happening and the shuffling happening in the sense that, okay, in the sense that some of the results from one machine is going to another, but for time being you can basically, you know, delete this section for in favor of, I'm sorry, okay, let's just forget this portion for time being, and we have just this one which basically takes you from here until here. All right, I'm just making it simple. Okay. All right, so in for fourth step, both will be combined. So your node 1 is containing this file, node 2 is containing this file, and we want it to be sorted. So what we have written in the map is the key and value will be prepared, like sa will be one key and value will be one. Whatever function you wrote here, there's the same thing. And once it has finished, it has finished. Okay, once it has finished, the data will be merged together and will be passed on to reduce. Okay, all right. So it will be passed on to the reduce and there will be results. All right. So here the same step what we were showing for the single machine, same step is happening for multiple machines. Map happened, then it converted into key values, the sorting happened on each machine, and whatever key were there, values were there, they were merged together and then shuffled and split it again to multiple reduces. And then some of the values went to one node, some of the values went to another one, then they merged together and the result came out. Okay, so same map reduce function which you saw that it was happening on here, same thing is demonstrated with the multiple machines. Okay, so as you can see that there was sare ga here and sare sa here. Basically same file split into two portions, and as a result, in the end of the map here, in the map here, these are the result. Basically, all your map function did was prepared key value, and value is always one for all. Similarly here, so it is up to you what you write. Basically, your problem, what exactly are you trying to prepare key values, and that is your control. That is the only control you have. Like you have to figure out what is my key and what is my value to be kept. All right. And similarly here, which is the third step, where sorting is finished, this data is sorted. Here, the data is sorted. Now, once that sorting has finished, the next step is that to do a shuffling, meaning keys from one node is moved to another one. Okay, from here this is sorted already, and now it is realized that it can keep ray on one side while can move sa to another one. So all sas are moved to another one, and these values are on one node. Okay, and once that is done, in as a step of the reduce, on the fifth step you will see ga1, ray1 and sa4. All right, so this is what is happening on multiple machines. Is it clear? Did I confuse you? Yes, shuffle is nothing but reordering and splitting again. How does how does Hadoop know how much how much to split and save in each node, and how is it computed? Okay, so Hadoop doesn't know it generally. So it just basically in the beginning it tries to say that I want to keep three keys on one node and three keys on another, and so on. So in the beginning it does a uniform split, equal number of keys. So same thing, like if you have seven RE and one GA1 SA, how will it be split done? So in the beginning, it tries to, you know, keep the rule of thumb is that it'll keep the same keys on the same node, right? And to do that, whatever in the beginning it will try to keep number of keys similar on one node, number of keys same all across nodes, and then it will also prepare heuristics in the backend so that in the future it can decide better. Okay, but I'm not I mean in these cases generally heuristics doesn't matter much. Okay, so mostly it will be equal. Can we configure the number of keys? Not really, not really. Okay, but you can configure how many reduce phase you want. By default there is a single reduce phase. Okay, it is up to you how many reduce phase you want. Okay, if it is only single reduce phase, then it doesn't need to, basically all it need to do is bring all the data from the second machine to the first machine and keep reduce only on the one machine. Okay, so that is the general case, then it doesn't have to resplit it, right? So this is what is happening under the hood for you, okay? And this is the group by clause. Now, should I explain it again, this diagram, or is it good enough for you? So, Prasanna, was I able to answer your question? Okay. Ishwar? So, Ishwar's question is that can we have multiple map phases? So, if you have multiple map phases, actually, so you want to say that after one map, you want to run another map over here, right? Is that your question? And then say you have got three map phases, one after another. Okay. So basically, why would you like to do that? If you were like to do that, you can actually as well combine all of your logic and keep it in a single map, right? In a single map. So because map invariably will be executed multiple times. So it will take a input file, pick up a line, and then run your map function on that line, then pick up another line, run your map function on that line, and it will keep on doing it. So I mean, generally a single map would suffice, but what would you require is more of a map reduce phases to be combined together to give a results. Okay, probably that's what you meant also, because the map reduce phase, you can have multiple map reduce phase. So once map reduce phase, you got the results, then you again the results are given to another set of uh, map reduce, then whatever result came in, then you gave that input to the another map reduce phase. All right, so that's what it is. Okay, any other question on this screen? So all I have tried to demonstrate that on each node there is a map happening, on each node map happening, and then each node is sorting their data, and then shuffling merging is happening of that data. If there is a single reduce phase, the merging will happen. In case more than one reduce nodes are there, you can specify how many reduce phases you want as part of the config, and then if there are more than one, then shuffling will also happen. Okay, and it automatically decides which how, I mean, it automatically decide where to execute reduce, and there again it tries to keep reduce as close to the data as possible. All right, so should I move on? So or should I describe it again? How are you guys comfortable with the map reduce definition? So basically, your role will be to think about what logic should go into your map function and your reduce function. What is it? What is it that map should do such that I can get I can get my results? What is it that what my map function should spit out key and value to solve my problem? Okay, that will be your role. Okay. Can we have a complex problem to be explained with the same MapReduce? Okay, great. Let us say, um, how should I describe? Let me just take a, because if the only examples I'm getting is actually the problems I'm going to ask. Okay, so give me some. Okay, So let us say that mm, I have actually 4 5 problems and I do not want to disclose right now. Okay. And okay, let us say that you have to find out uh, the let's say that you have to find out the 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 length distribution in English words. Okay. Say all you want to do is how is the word length distributed across the words. Okay. Okay, let me just take this example, right? Say you have got Sandeep. Its length is how much? Quick. 7, right? And then you have got Sanjeev. Its length is 7. Okay. And similarly, you have got Sen, whose length is 3. Now, given a lot of word, your role is to find out the find out how many words exist on a same length. At the end of day, let's say in this case, you have Giri, you have say Ram, right? So you have to tell at the end of day that for length of 7 we have got how many words? Quick, how many words? 2, right? For length of 3, how many words we have got? For length of 3, how many words we have got? 2. Excellent. For length of 4, how many words we have got? 1. Excellent. So this is your objective. Given a lot of data, you have to tell for what is the length distribution across this data. Word length distribution. So what will you do? So first step will be to think about what are we trying to do. We are trying to find out, we are trying to count the words which are of the same length. Okay. We are trying to count which are of the same, count all the words which are of the same length. So in the map function, what am I going to do? What am I going to do is take for each words, okay, for each word in my input, whatever input is given, I will say print length of my word. Okay, length, let's assume that there is a function and I say 1. Okay, so this will basically convert my convert my input into, say, uh, uh, my I mean this is my answer, this is what I'm expecting. Okay, my map phase, this map phase, what will it give out? Can you somebody help me out with the values? What will be the output here? Key is the length and value is the list. No, here the map, what will be the list of values quickly? No, that will be after Hadoop has taken output. After Hadoop has sorted. So it will be 7 space 1 and 7 space 1 and then 3 space 1 and then 4 space 1 and 3 space 1. This is what will be my map reduced output. Now Hadoop will take this output, take this internally. This is what happens inside Hadoop. Okay, this is what happens inside Hadoop, and you will be having 7, and then say 1 comma 1, okay, and then 3, or you can first say 4, 4 versus 4, 4, 4, and then we have got only 1, like this. Okay, this is what Hadoop does for you. So MapReduce only gave these key values. Hadoop internally did sorting and then aggregated values together. And then your reduce function will be executed on each. So your reduce function should look like what? So your reduce function has a word and an array, and all it need to return is sum of your array. Okay, that's it. And then you will have your output. This output you'll get. Okay. Or let's say you're trying to figure out an average, so you can do an average. If your problem statement is that find out the average length, okay, sorry, average number or something of that sort. Okay, was I able to explain, Ishwar? Okay, Prasanna, okay. Okay, so Prasanna has got a point here. So mostly, I mean, it is generally ascending. Okay, it is generally ascending, and this is just a mistake for giving an example. Okay, so internally it is generally ascending, and for an end user it doesn't matter much. So by default it is ascending. Okay, and this is configurable. Okay, now I'll just go quickly through the exercise. Okay, think about these problems by when we meet tomorrow again. So same problem, like big text file, and you have to find out frequencies of the letters. Instead of finding frequency of the word, you have to find out frequencies of the letters. Okay, this is a very common problem. Whenever you do a literature analysis, you try to do a lot of frequency analysis of the letters. Now, do you need MapReduce in this case when you are doing frequency analysis? Frequency analysis, counting number of times A came in, B came in, C came in, and Z came in. That's all. Okay, up to A to Z, you have to count how many characters, how many times a particular character has come in. Okay, once you have done that, you're, I mean, that's the objective of this file. So if you have to find frequencies or number of times a particular letter has come in a text, in a huge text, do you need MapReduce? That is my first question. Second question is that in a given huge text file, find anagrams. How will you do that? Okay, anagram is anagram is basically rearrangement of the letters of the word. For example, the cat act in the tic-tac-toe, and the output is, and here the output will also be the, okay, and there is nothing here. Okay, and here you can say the, and then and so on. So, okay, so effectively all I'm looking for basically, which here cat, tack, and act are basically rearrangement of the same letter, and therefore they are the anagrams. So how do you find anagrams in a huge text using MapReduce? Second one is a file contain DNA sequences of the people. Find all the people who have the same DNA. Okay, so these are the few questions which I'm leaving you with these. Okay, and two people belong to the same family if the inverse and the forward is same. Okay, like this. Okay, so go through these problems and we will discuss them again tomorrow. Okay, think about these problems in deep, all these four problems, and then we'll discuss it tomorrow. All right. So that's pretty much for today. All right. So go through these four problems. Okay, go through these four problems and we'll discuss it tomorrow. All right. Meenal, Prasanna, Karthik, Jagannath, Ishwar, Akhilesh. So basically go through all these four problems and we will discuss in detail. And why this is very very important because this will give you a clarity on how to convert any problems into map reduce phases. No, till four. Go through the fourth one also. Okay. Yes, yes. I'll provide the access to the slide. Just go to the my courses and I will immediately enable it. Okay. Okay, I'll immediately enable the second session content while the video will be available by tomorrow evening because it takes time to upload. Okay, now that's pretty much it. Okay, just go through these problems. These are very important problems, and you should go through these all of these. Okay, good night then. Good night for me, and thank you all. And let's meet tomorrow and go through these problems. Think about it. How will you solve the using MapReduce? Okay. Thank you. Good night. Bye bye. Good night.